Hi, everyone. Welcome to the second part of our second lecture of Astronomy Geoscience 160. This lecture will consist of a discussion of what temperature is, what ions are, and what radioactivity is. So the main question I want to get at to start is, what does it mean for something to be hot? Of course, we all know what hot feels like. We've all burned our hands on a hot stove, and we've all felt the warmth of the sun on our skin. But what exactly is going on when something is hot physically at the microscopic level? So this is a video of what milk looks like under a microscope. Milk consists of water, which is mostly clear in this case, with big fat globules, so large chunks of fat that are suspended in the water. And if you look under a microscope, what you can see is that the fat globules are jittering around. And the reason that they're jittering around is because they're constantly being bombarded with smaller things, in particular the water molecules, which are too small for us to see with this microscope. So what's happening is something that looks like this. So imagine that these copper beads that are being vibrated by this stereo are the little water molecules. And they're crashing into this big fat globule that is much larger and much more massive and moves just a little bit every time it's hit by one of the smaller, faster moving particles. So what you can see is that everything in this liquid is constantly in motion. All of the molecules are constantly jittering around, crashing into the fat globules. And it turns out that when we talk about temperature, when we talk about something being hot, what we mean is that hot things tend to move around more when they're in this state. So if you have a hot liquid, the water molecules will be moving around faster than they would be if the water was cold. So here's a way to illustrate that. This person has created two beakers of water. On the left, they have cold water, and on the right, they have hot water. And they're going to drop a drop of food coloring into both. And you'll be able to see the difference between the two and which one shows the most agitation. So these droppers full of food coloring, they're essentially dropping big pigment molecules, big red molecules, big blue molecules into the water. And those molecules are getting bombarded by the smaller water molecules. And you can see immediately that the hot water is expanding. The pigment is getting dispersed much faster than it is in the cold water. And that's because the water molecules in the hot water are moving around much faster than they are over here. They're therefore jittering those larger pigment molecules and causing them to disperse faster and move around throughout the liquid faster. And you can see that after just a short period of time, these pigments and the hot pigments are essentially distributed throughout the glass of water. Whereas over here on the left, not much is even happening with those with the pigments in the cold water. So atoms in hot materials move faster and collide more often and more violently than atoms in cold materials. So what happens if an atom goes too fast and crashes into another atom with too much speed? Imagine you have a really, really hot substance, such as hot hydrogen gas. And you have a hydrogen atom here, a proton and an electron, and it's going to get hit by another proton and electron hydrogen atom. In some cases, if this is going fast enough, the collisions are powerful enough to essentially knock off an electron from the proton. And now instead of having an atom, you have what's called an ion, which is an atom that has either lost or gained an electron, and a free electron, an electron that's just going throughout this gas. This process is called ionization, and it preferentially happens in hot gas. So this is a graph that shows in a gas made of hydrogen, what fraction of the atoms are ionized at different temperatures. So the y-axis is showing what fraction of atoms are ionized, and it goes from 0 to 1. So 1 means every single atom of hydrogen is ionized. There are no atoms of hydrogen that have both a proton and an electron. They're all split apart and they're all separated. And 0 means they're all in atom form. They don't have any that are ions. They're all together. And it turns out that if you get to a temperature of roughly 10,000 Kelvin, which is the unit of temperature, the unit of heat, essentially, that astronomers and physicists use to describe things, it's similar to Celsius, except it has a slightly different 0 point. So if you get to 10,000 degrees Kelvin, essentially you have a 50-50 shot of your atoms of hydrogen being ionized or not. This can happen for other elements too. It's the same process basically. If you have a larger atom with more protons and more electrons and they collide, then sometimes you'll get free electrons that are shot off. So the process of ionization can split apart atoms, but it turns out this isn't the only thing that can happen. If you add more and more energy, it turns out that nuclei can split as well. So instead of just having an electron get shot off from this atom, you can actually have a nucleus become split and lose a proton or a neutron. In general, this is much harder than it is to ionize something or even to break apart a molecule. Just think about how much force must be holding these protons together. In the first lecture segment of this second lecture, we talked about charge and how protons are positively charged and they're all positively charged close by to each other. Like charges repel each other. So all of these protons are trying to get away, but they're held together by something very, very strong. And if we want to split the nucleus, we have to be able to overcome this as well. So it's actually very difficult to split nuclei. But it does happen in some cases. There are some elements that naturally leak stuff out of their nucleus just sporadically. We call these radioactive elements. So the idea here is you have a really, really big nucleus. The larger your nucleus is, the more protons and neutrons it has, the less stable it is, and the more often you'll see that it becomes radioactive and starts spontaneously losing protons or neutrons. So here's an example of a uranium nucleus, which is a big, heavy atom with lots and lots of protons and neutrons. In particular, this flavor of uranium has 235 protons and neutrons put together. And in these cases, what will happen is your nucleus will occasionally shoot off something. So here's an example of one of these so-called nuclear reactions, where you have a big, heavy nucleus, in this case, a nucleus of the element radium. The way we're showing this here is we're showing the element name, radium, and we're showing how much mass it has. So essentially, how many protons and neutrons make up that nucleus. And in this radioactive decay reaction, the radium atom changes into a radon atom and it shoots off a helium atom, which is also called an alpha particle. You can notice here that the total mass seems to be very similar between these three. You're not really changing the total mass very much, if at all. So the mass of this atom here is 226 proton masses, essentially. This is 222 proton masses, and this is 4 proton masses. The total mass is almost the same, though. It's not exactly the same, because if you look in detail and you figure out exactly how much these atoms weigh, these nuclei weigh, it turns out that the final mass, the sum of the radon nucleus plus the helium nucleus, is a little bit lighter weight than the original one. In fact, it turns out it's a little bit lighter weight by about 0.005 proton masses, so about half of 1% of the mass of a proton. And it turns out that where this mass went was that it was converted into energy. So Einstein wrote down the famous equation E equals mc squared. Energy equals mass times a conversion factor squared. And what this says is that sometimes mass can change into energy and vice versa. And that's exactly what happens in the case of radioactive decay. You can get a little bit of mass converted into energy. And that energy goes into accelerating the particles that shoot off of these nuclei and cause them to go at very, very high speeds. It turns out that this is why radioactive materials are harmful to our health. These materials are essentially shooting stuff at us. They're shooting atoms. They're shooting nuclei, they're shooting gamma rays, all of these kind of harmful things, and they're going through our cells and ripping our DNA. So that's why we generally try to stay away from radioactive materials. So those materials, like radon, naturally decay and naturally produce neutrons and protons and helium atoms flying out of their nuclei. But we can actually deliberately cause nuclear reactions as humans ourselves. One way that we can do it is by shooting stuff at big, heavy nuclei. So, for example, if you shoot a neutron at very, very high speeds towards a uranium nucleus, then that can create an unstable nucleus. That neutron is lodged in here, and it just is too big for it to hold together. And what happens is this nucleus splits into two. This uranium nucleus splits into krypton and barium and releases quite a bit of energy. And you can actually take advantage of these nuclear reactions because in some cases, like this one, it also produces 3 neutrons. So if you're clever, you can see how this situation might be useful to cause more reactions. Because now that you have 1 neutron coming in and releasing 3 neutrons, then each of these neutrons can cause another collision with a uranium atom, cause it to split, and then release 3 more neutrons. This is what we call a nuclear chain reaction. And this is the idea behind how nuclear power plants work. You want to carefully control the number of neutrons that are flying around in an area with a lot of uranium. And as they do this, they split the uranium, they release energy, they heat up the surrounding material, which is then used to drive essentially a steam turbine. And in the process, they release 3 more neutrons that continue the chain reaction and continue releasing more energy from more uranium. But you have to be careful with this because if you triple the number of neutrons coming out every time, eventually you'll just release more and more energy exponentially. And it will become so fast and so unstable that you can sometimes have your entire reactor melt down. And that's exactly what happened at the Chernobyl disaster in Ukraine in the 1980s. The nuclear reactor was in this building. It got too hot because the chain reaction got out of control, and it essentially melted the entire building and spewed radioactive material across much of Europe. And sometimes people want to make these chain reactions run out of control on purpose. And this is how nuclear weapons work. They essentially create these out of control chain reactions and try to accelerate them as much as possible to release tremendous amounts of energy.